Welcome back. We're just about to start our next session. All right, well, welcome back. I hope you had a good coffee break. So I'm going to introduce our next panel, our first panel of the day, actually, which is ISS as a test bed for missions beyond low Earth orbit and onto Mars. And moderating our panel today is Sam Scimemi, who's deputy of ISS at NASA. And I should note that in many ways, Sam is the co-founder of this ISS and Mars series we've been running. We brought this concept to NASA about a year and a half ago, and talked to Sam, and he's been one of the key people in making this possible. So thank you very much, Sam. But Sam has had 25 years in human spaceflight experience. He's worked at 4 NASA facilities, including headquarters, Johnson Space Center, Ames, and Goddard Space Flight Center. And his career has encompassed real-time operations, flight software development to testing, international partner negotiations and integration, system engineering, end-to-end testing, and policy and programmatic management. So, ladies and gentlemen, Sam Scimemi.
Thank you, Chris. I'd like to ask my panel to come up to the table, please. All right, thank you all. First, I'd like to introduce George Nelson. He's from the ISS Program Office down in Houston, and he's a manager for the Technology Demonstration Office. Next is Mike Rodriggs. He's the iStar mission manager there at the Johnson Space Center, and you'll hear quite a bit about what's going on there. That's the Mars analog portion of our discussion. Scott Copeland, he's the director of ISS utilization from Boeing down in Houston as well. Tsuyoshi Ito from JAXA. He's a program manager and management and integration department. He's also a flight controller. And Diego Urbina, who participated in the Mars 500 from ESA. This morning, you heard a lot of context. Can we get my presentation up, please?
Yeah, he's coming down.
Oh, okay. Real-time ops, you got to be flexible. That's right, we can. All right, thank you. This morning we heard a lot about the context of going to Mars and the importance of it. But this panel is going to address sort of more of the nuts and bolts about using space station, what we got today, and how we realize getting a mission to Mars from the other end. You can look at Mars as the objective, but then flip it around the other side of the coin and say, well, how do we get there based on where we are today? So I'm going to set the, sort of a context for that, and the panel members on my panel will start addressing those lower level items, and the rest of the conference will address even a broader perspective of even missions and all the political ramifications. A little bit about where Space Station is today. As many of you know, the station is a multi-agency across many countries. I don't even remember how many countries it is today. It's, of course, with the U.S., Russia, Europe, Japan, and the Japanese space agencies. This program started back in 1984 under President Reagan with an initiative to bring in friends of the U.S. at the time, which was Canada, Japan, and ESA. And then in 1994 we started cooperation with our Russian colleagues. A little bit about what Dr. Gardini said this morning about our partnership. Yes, it was rough going in the beginning. Like any complex relationship, it's not always easy. But I can tell you this, what has been expressed many times is that the strongest thing that we have in this program is the partnership. It is deep, it is broad, it's not just on the surface of an interface, it is basically we've gotten into each other's life on this program. We've been permanently crewed since November 2000. We've been crewed for quite a long time now. Today we have more experience than the MIR program had, and it's of course been much broader and which a much more complex vehicle. We're supplied by crew and cargo by across the partnerships with multiple vehicles from Progress, ATVs and HTVs, and we're of course relying solely on the Soyuz now for crew. Bit of a scale. Space station is as large as a football field, whether American or European. It's over 450,000 kilograms. It's quite a large complex. It's got a habitable volume of an American 5-bedroom home. It's the largest space power platform that's ever been developed, about 85 kilowatts. And as far as research and technology development capabilities, we have 24 pressurized rack locations and 25 unpressurized locations out on the truss and on the modules. And of course, we've got ground control centers across 8 countries. So imagine the complex international cooperation and integration that has to take place just to pull off real-time operations 24 hours a day, 7 days a week, every day, every year. So you might ask, why is exploration of Mars linked to the ISS? When we first started this series with Chris, many people were skeptical. How in the world can you link station and ISS? And the human aspects, everybody got. Everybody understood doing human research on human health and exercise and radiation effects. Everybody got that. But the real link is in this picture. And it's not always apparent what it is. It may be some technology, it may be some communications, but what is it really? It's our near proximity to the Earth. What dominates the space station program is the Earth. It's near proximity and its resources for people to access the space station. So if we talk about the challenges leaving the near proximity Earth, how can we start to dissect that up? And I'm going to give you one cut through this multifaceted problem. Let's start with Mars. Mars is, on average, 228 million kilometers away from Earth. On the shortest duration of a transit time, it's about 2 years transit time. There's several mission scenarios, anywhere from 2 years to 5 years, but for the shortest, it's about 2 year transit time. And the communications round trip can take up to 42 minutes. And that's the only link you have. That's the only tether there is to the Earth. There's no additional resupply. You got to take everything with you or pre-position it. There's no chance to come back basically once you've passed about 2 months. If you take a look at that and look at space station and do a comparison, space station is only 390 kilometers on average. Pretty doggone close. This is not the scale, of course. It's about 2 days transit time back and forth. And communications are near term. But this isn't the only tether we have to the Earth. This is the real life of space station. The crew exchanges we have every 6 months, the crew supplies and logistics that come up on a regular basis. We have crew and atmospheric samples to come back to do the research and to keep the crew healthy. We have modified hardware. When things break and we have a design problem, we can fix it and bring up new hardware. And also we have emergency crew return practically any time. And one thing that's really overlooked, that's extremely important on space station, is how do you get rid of all the trash? And on a trip to Mars, all these challenges will have to be overcome, and station is the place to address all these challenges. And you'll hear from the panel on addressing many of these challenges. So to go to Mars, you actually have to build a unique capability to live away from the Earth. Unique in that you can't, this is not the Earth providing you resources, it's some man-created or human-created capability to live away from the Earth. And for space station, it's like extreme car camping. You can always go back to the hospital, you can always go to Walmart, you can always go back to get what you need, but going to Mars, there's no chance. You have to have everything with you, you have to prepare for every failure scenario and all the risks. So how do we break this dependency on Earth? Today I'm just going to, in my presentation, just address the habitation and long-duration spaceflight gaps. There's other gaps as presented earlier in propulsion and other areas, or launch capability. But for space station proper, I'm going to address the following gaps. First is the obvious one, which is crew health. We have a human research program today across the partnership that's addressing the radiation effects, how to prevent bone loss, and things of that nature are all being studied today on space station. Again, microgravity and radiation countermeasures, as far as the crew exercise equipment and the like, all those things are being developed, operated, and changes are being sought to improve those capabilities. The next one, life support and environmental monitoring, that gets a lot of attention. You'll see that ESA, NASA, and JAXA, and of course the Russians all are working on or have environmental control life support systems. EVA systems. This is unique, of course, to human spaceflight. It's been critical in the past and is expected to be critical in the future. I'm sorry, I've been advancing the slides here. That will continue to need to be evolved and from a system that's maintained on the Earth to a system that's be able to be maintained in space. And of course, operations beyond near real time. Our entire experience, including the lunar Apollo program, communications were all near real time. So what is station doing about that, all those things, the station program and the partnership? Of course, I mentioned earlier, we have the human research program that's addressing all the crew health and countermeasures. We're also addressing through our AES program inflatable habitation technology to possibly address radiation effects. Of course, radiation monitoring and protection. We have several programs across the agency that are looking at active real-time radiation monitoring, and of course, how do we protect the astronauts or develop countermeasures to mitigate those risks. We have ECLIS reliability and operations performance enhancements that we are working on right now to address the shortfalls we've had in our current ECLIS system. The Russian ECLIS system, mainly the Electron, has years and years of experience, and our Russian colleagues know exactly how that works from many of the years of Mir and from previous experience. So they know exactly how this thing works, they know exactly how it fails, and they can go on and replace those systems. We're still learning on our side. We're working on our next generation EVA suit here at NASA to replace the current about 45-year-old technology. We're working on, you'll hear about autonomous crew operations. Our Mars analog simulations. I know the Mars 500 is having their conference, I think, next week on the outputs of that, and we are participating in that conference and trying to learn how to apply those lessons to space station operations. We have material testing going on space station today for long duration exposure. We're also considering fire safety experiments and demonstrations. Today we know a little bit about how fire reacts in space, but only from very small enclosed combustion experiments. We do not have actually large-scale experience in fire safety. Of course, telerobotics, we were doing quite a bit now with of course, the station was assembled with the robotically. We're now doing maintenance activities with the SPIDM, and we are working on the Robonaut 2 to be able to provide those type of operations as well. And of course, deep space navigation. Being in proximity close to Earth, we have GPS, and thank you, the Department of Defense, for that. When we go beyond, however, when we go beyond low Earth orbit, we no longer have that. So we are developing an experiment to use X-ray navigation for precision navigation in space. Of course, beyond all the technology, the space station itself, the program itself also can be used to move forward in our exploration endeavors to fill these gaps as well. So that's all I've got as far as the setting the stage, and I'll ask the first speaker to come up, George Nelson.
Okay, thanks. Well, good day to everybody. Do I need to start my presentation?
Yeah. Is there tech support somewhere? You got it? Okay.
All right, well, I passed that test. Okay, well, so as Sam mentioned, I run the Technology Demonstration Office for the ISS program for NASA, and we'll talk about the difference between how we do it just from the inside the agency and through the IPs and all of our partners. Since the last time this forum met in the spring of last year in Washington D.C., we've retired the space shuttle, and so there's no more. Let's making sure we have things pre-positioned. There's no more semblance of assembly operations at this point, and so I'm here to make sure that you realize that the ISS is very much open for business, and that's the main task of my office and the offices that complement it. We've been utilizing the ISS for quite some time, and so all the planned experiments and all the existing and past ones, you can reference those on the web at that link right there, nasa.gov/ISS-science, and if you click on experiments, you can get some good high-level information for everything that's done up there, and it's a greater number than you would expect, and it's well searchable. If you even just search on an experiment name, it'll link to this page for you. So a good resource there. For the United States, we have the National Laboratory and my office, the Technology Demonstration Office, and they're kind of running partners, and they complement each other so that depending on who you are and what type of research you're trying to do, that you have an avenue in, and both those offices act as a front door for technology specifically. The human research aspect is another office, but when you're talking straight technology, it could be either one of those. And so the difference between that is the National Laboratory Office, that provides utilization opportunities for other U.S. government agencies, as well as private citizens or private companies. Any U.S. taxpayer that helped foot the bill to develop this platform has access to it. So as long as you identify the need for the ISS environment, then you don't have to feign any altruism, is the phrase that I usually use. If you can prove that you have a good business case and it's enhanced by the utilization of ISS, then we'll fly it for you. However, when it comes to the realm of this discussion that we have here today, private citizens or private companies that want to improve or prove their space technologies on orbit to give themselves a competitive advantage for later on, whether selling it to governments or to private industry as private industry comes online, it's a really good opportunity to leverage the investment that all of our countries have made in the ISS so far. So That's slightly different from my office. So this is all within the term utilization. So that's what we're trying to do, is use the space station to its fullest extent. And when we look at utilization, we have particular investments that the agency itself makes. And so those are the experiments that we try to flow through my office. The difference between this and the National Lab is we've set up a private entity with National Lab in order to vet and prioritize those specific payloads that come through. However, NASA trusts itself to prioritize its own investments. So if it's an experiment, if it's an investigation, if it's something that NASA has at least partially funded, it will come through my office. And so those are things that are paid for by the Office of the Chief Technologist, HEO Mission Directorate, which has the space station, formerly the Space Shuttle, and the future exploration options within that office. Advanced Exploration Systems is a subset of that HEO Mission Directorate. And then the Science Mission Directorate has many payloads, particularly the outside ones, either looking up at the stars or down at the Earth, that also flow through our office administratively. And then we help out with the Department of Defense payloads as well. So there's the exception that proves the rule on the National Lab, Tech Demo Office delineation. Most of the DoD payloads are decidedly technology driven, and so those flow through us rather than through the National Lab, and their CASIS is the not-for-profit entity that has been set up to help vet all of the proposed demonstrations or investigations on ISS that are National Lab. So it's important to understand, and I think most of the people in here do, but it's worth reiterating that ISS is a pretty unique vehicle, and obviously never before, and it doesn't have an infinite life, and so we think it's all of us think it's pretty important to take full advantage of it now. And it provides some pretty significant opportunities, and it does so by having some pretty significant capabilities. So the platform itself, if you're an investigator, will provide you with power, data, and thermal considerations for wherever you happen to be, pressurized or unpressurized. If you're looking for the microgravity environment, then we've got it. The program itself, the ISS program, will take care of integration and transportation to and from low Earth orbit. So when you look at the cost of an investigation, typically that is a really large chunk of your budget is just upmass. Well, if you get approved through either the CASIS option or through my office or through Human Research Program, we take care of that for you, which is a pretty big deal. And you'll end up getting a ride on any number of the ISS assets that we have in the fleet. They're, ATV from Europe, HTV from Japan, Progress and Soyuz from Russia, and then we have commercial providers coming online with SpaceX and Orbital. So in addition to all of that, we have people there. So even if you could afford a free flyer that they would be able to take whatever you were investigating to low Earth orbit, there's the added advantage of having crew there to either perform the investigations for you, repair it if there's a problem, observe it if that's what's required, modify and interact with it. All these things are covered by the program itself. So there's significant investment that's been made, and leveraging off that investment is something that we hope you do. So Sam mentioned the research facilities that we have. We're familiar with the internal and the pressurized modules, and then here's just a quick look at a lot of the external options that we have. There's the 4 ELCs that are out there. There's also the external facilities on the Columbus and the Japanese module. The Japanese module allows you to fly things up pressurized and then pass them out through an airlock to take advantage of the atmosphere and the environment in low Earth orbit. And you can see the GEM facility on the bottom right, Columbus in the center, and the ELC while it was still in the ground on the bottom left. So I've been talking mostly about how NASA's doing this ourselves, but we've been, as an international program, trying to make sure that we do this in an integrated and international fashion. So while we've always been considering it, over just a little over the last year, we've made some concerted efforts to discuss the need and how we're going to execute, demonstrating and improving a lot of these exploration technologies by using the ISS. A couple actions from the highest levels of the program to all the partners to hold these discussions and to form teams to look at how we're going to do this, how we're going to plan so that we can have a performance to plan and not get to the point that we finish this program and say, oh, I really wish we had taken care of X, Y, and Z because A, B, and C are just fine. So in addition to that, we're looking at the proper utilization of resources that are on the ground. So we all know the economic environment that we're in. So all the international partners are looking at what the smartest options are for collaboration compared to those options that are best suited for not necessarily competitive demonstrations, but dissimilar redundancies. If we're talking about the transit time that Sam alluded to earlier, dissimilar redundancies are probably something that we're going to want regardless. And as we make the investments now and evaluate what the best ones might be for later, looking at multiple options is probably prudent. So we've been looking at some specific areas, but they include, they're not limited to, but they include these ones that you have listed here. Advanced life support systems is one that we've already heard mentioned today, and you're going to hear that consistently. The ISS ECLSS systems were designed to be where they are, in low Earth orbit and serviceable, accessible, using upmass. The future systems that we use for Mars transit are not going to be able to take advantage of that, and so there are some necessary changes that we'll have to make. Just in mass is a really easy way to advance the state of the art that we have now. Advanced power and distribution. I think we have a couple of discussions here in these 2 days that talk about propulsion. With electric propulsion, you're gonna need a lot more power than even the ISS can currently provide. As Sam said, it's the biggest electric platform that we've launched, but you need something significantly in excess of what ISS produces to be able to have a lot of the solar electric or nuclear electric propulsion options. Robotic tools, systems, and operations. We have, as Sam said, performed many robotic operations on board, but those continue, and we'll talk about those, and I know there's some examples on the panel that will follow. Crewed spacecraft operations support tools. You're going to hear examples of those. Common nav systems, very important as you get away from TDRS, away from GPS. Human health and protection. You'll hear examples of what's necessary. A lot of this focuses on radiation. Cryogenic operations. Well, if you're not doing electric propulsion, or even if you do, there are many scenarios that involve also some chemical propulsion that complements that, and so that's going to be important. And thermal management is always important in that environment. So some of the examples of things that we're already doing on board ISS, the Robonaut, the team on the ground for Robonaut is really starting to hit its stride for ISS operations. But the robot itself, I think, hasn't yet hit that stride. And it would help to hit that stride when its legs finally launch next year. So it's already been doing some tasks on orbit, and it picked up even just very recently one of the more mundane tasks that the crew would love to have it take over full time, and it also happens to have the only pan-tilt cameras in the pressurized volume of ISS. So they've even asked, hey, could you look around? And so the Robonaut would look around just to help ground controllers in that way. So there's a whole lot we can do, but it really focuses on crew assist. So there's been discussions: do we just send robots to Mars? Do we send people? Regardless, the Robonaut is sitting there as a crew assist type of thing, and we think that's likely where it's going to have its its greatest impact. I'll do a quick aside right here. There are many of the things that the Robonaut is doing that doesn't necessarily only help future exploration missions and things on the ground. So the type of work that Robonaut does gets proven on ISS and is necessary for ISS, but then ends up having benefits here on Earth. And sometimes that's our best selling point for the investments that we make is how it really helps people here as we keep going. And in the next few years, I would expect you to see some things that you'll recognize as benefits stemming specifically from these investments. We talked about the environmental control and life support system. So a mean swing bed is one of our first attempts at another paradigm, another option for carbon dioxide removal on orbit. That's there now. Spheres has become, while it started as a standalone experiment, has become its own facility in some ways, and an adaptable one at that, as it starts to use new options like a suite of smartphones that can go up and further interface and control and become part of that facility. And so from future desired capabilities like EVA inspection or autonomous rendezvous and autonomous coordinated flying, there's a whole suite of investigations that Spheres takes over. You'll hear from Mike Rodriggs right after me, and the iStar on-orbit operational simulations that we're looking at. It's the only place in space that we got right now to look at how the crew can interact and interact less when required and be more autonomous. So we're taking advantage of that. The robotic refueling mission, you've heard likely some of their recent successes. There's follow-on investigations with that, but that's been successful so far, and that falls into the cryo operations that we discussed. And then you don't hear, it might not be intuitive to think about any surface operations being analogous to an orbiting platform, but we've even investigated some crew control of surface telerobotics, and that's something that's coming up in the near future. It's one of the many options would be from an orbiting platform for a crew to drive a rover either on a lunar surface or a Martian surface or a Martian moon as a precursor to landing, and so that explores that option. Some others that are in the pipeline and coming, well, we've already started a lot of DTN work, and that's been across agencies with JAXA, Russia, and ESA. Delay disruption tolerant networks are going to be important as we get further and further away. OPALS is an optical laser comm investigation, and that falls into what both I and Sam mentioned as one of our priorities for comm. He mentioned the X-ray navigation. That's the sextant investigation here, and so that's in development. Sort of a galactic GPS. And then Connect Scan looks at user-defined radio, so that is also a communication thing that is never going to be lost as an important factor for any crew who's going that far away. So I'll come close to closing here by saying that there are some exceptional opportunities to utilize ISS in the nearest term. Between now and 2016, when the majority of the decisions will be made on extension after 2020 of ISS, there's, as I said, exceptional opportunities to utilize the vehicle. So there's going to be a great push to find where that maximum utilization is going to be. I don't think we found it yet, and then to completely fill the full capabilities of the ISS, whether that's adding another crew member or fully utilizing the upmass that we have. The opportunities are going to be there for you. So in the nearest term, we're going to have a lot of long lead item developments that are not necessarily going to be there tomorrow. So if you particularly have options that are nearer term investigations, not only can you get them done, but we are eager to help you get those done. So ISS has the capacity, and all we're missing at this point is you and your good ideas. So if you'd like to contact anybody in my office or the Research Integration Office, which houses the Program Scientist's Office, the National Lab, as well as me, please do so. There's multiple contact points up here. Mary Beth Adine runs the National Lab, but she will probably vector you to CASIS, the link to which is under the World Wide Web links there. And we have some efforts for social networking that can keep people up to date. So if you prefer to get updates that way, we have those options. So, see, that's all I got.
Thank you, George. Mike?
All right, before I begin talking, as Sam and George said, I'm Mike Rodriggs. I'm the manager for the iStar. So I'm going to break this already. For the iStar office, we're not tied to space station. We're the ISS. It's an analog program looking to use the space station for analog research to get us to Mars. I cut my teeth in my career in space station, and so I'm very proud of the work that's been going on in space station. And kind of emphasizing what George just said, there's a lot of activities going on right now, and we can benefit from your guys' input too. But I wanted to show you a quick clip of some of the stuff that's been going on recently in space station. This is from Expedition 29 from last fall. It's about a short 2-minute video, and it's just a really nice video I wanted to share with you all. So again, I just wanted to show off a little bit about space station and what we can do there. There is a lot of work being done right now, and we have a lot of potential. So I wanted to talk about iStar and how we fit into the picture here. So let's see, is this the, that's the clicker. Okay. All right, let's see. So these are the things I'm going to talk about, what iStar is doing, a little bit about analogs and how we fit into that analog piece. We'll talk a little bit about a Mars simulation using the space station, and then we'll talk about our 5-year plan. We have two real key areas of emphasis. We're part of an integrated analogs program, and we'll get into more details that here shortly. Taking a look at technology and operational development efforts to look at exploration and answer architectural questions in issues, but could use the space station to accomplish that. The other thing we're looking at is a Mars simulation planning and execution to help us get to Mars around several years from now, but the simulation to be full up conducted around the 2015 timeframe. All right, so the analogs. To prepare for deep space exploration, NASA has established several analogs to accomplish that. One of them we have is called NEMO, the Extreme Environment Mission Operations. Here, aquanauts live in an underwater Aquarius laboratory, and they have a variety of test objectives to simulate EVAs, navigational communication, integrated human robotic systems, and remote science and medical operations. Another one is research and technology studies, RATS commonly referred to, but basically looking at planetary analog missions, looking at reliable and cost-efficient tests to validate some of NASA's next-generation human exploration concepts. This is medium to high fidelity test readiness levels, and they're looking specifically to enable future human exploration capabilities by maturing the operational concepts and technologies through these demonstrations within field. We also have an in situ resource utilization analog. It's a planetary analog mission also, looking at hardware tested under stressful environmental conditions. Here you see some equipment being tested in Hawaii. The idea is to expand the integration of science technology here from an in situ perspective. All right, then we have ISTAR. This is where we fit in. We are a reduced gravity analog mission. We're going to be looking to use this space station as a platform to conduct a series of tests relevant to human exploration beyond low Earth orbit. Our first mission started around 2012 with increments 31, 32 doing some experiments for ISTAR. We want to understand and reduce human spaceflight risks. We want to prepare for autonomous crew operations for deep space missions. We're going to exercise the ground elements for training and technology development. We're going to test the space exploration concepts and technologies. And the idea is to continually produce scientific improvements to exploration system design as we move outward beyond low Earth orbit. All right, how do we do that? How does the analog program execute that? Well, the first thing we do is we take a look at the design reference missions and architectures that have been considered. So we're looking at Mars missions. Here's an example of some of the roadmaps that we have for Mars missions. We look at asteroid missions. Again, here's a roadmap that takes us to an asteroid and back. And then we break it down and try to take a look at what human and architectural risks are involved. What questions need to be answered? What are the technological gaps that need to be filled, both within the system development as well as in the human research program as well. So we take a look at the priority gaps that are missing, and we try to use technology or look into technology that can benefit from space station to fill those gaps. We start to answer these questions on technology, again looking at space station to see what can be used to help answer these questions. Also within the human research program, dealing with astronauts in space, what are their specific impacts? We talked a little bit about that today with radiation and other issues. And then we take those questions and the technologies, and through an integrated analog process, we take a look and see where it makes sense to test those. Sometimes it makes sense to test them in a NEMO environment. Sometimes it makes sense to test them in the RATS environment. Sometimes it makes sense to test them in the ISTAR environment on space station. And so what we do then is we break out where those technologies make the most sense. ISTAR will take a look at some of the exploration aspects of it. And then we utilize George Nelson's office, the ISSP Tech Demo Office, and pass all our information through that office for their consideration to see if it indeed makes sense to go to space station or not. And then we start the whole process over again. With the information that we get from these tests, we see how it affects the design reference architectures and see if it specifically reduces those risks and answer those questions, and we iterate until we've helped improve that design process. Some of the experiments that ISTAR has looked at include operational impacts of communication delays, greater automation of ISS procedures. Dr. Ewald mentioned earlier about the user-level procedures that the astronauts are using on space station. when you go to Mars, you go to deep space missions, you're going to have a lot more autonomy between the crew and the ground, so we're looking to have the crew do more functions on the space station without the use of the ground. We looked at noise environment mappings, small active radiation dosimeters, battery-powered medical oxygen concentrators, a variety of things. When they're ready, what we do is as I said, we use the ISSP Tech Demo Office, and they take a look at all of these to make sure that their readiness for this demonstration. They look at the funding profile, they confirm there really is a need to test this on space station, and then they evaluate the parameters, launch constraints, etc., to make sure that it makes sense and make sure that it's safe as well. All right, the other piece that ISTAR deals with is looking at using the space station as a Mars simulation. We have a long-term process to try to conduct this by 2015. So initially what we're doing is we're taking a look at the current ISS operation and activation for Mars missions. We're assessing what we can do right now on space station. We're starting to introduce specific Mars operational changes, more autonomous displays, more autonomous procedures, implementing communication displays, and other things. The next couple of years, we're looking to incorporate more discrete Mars forward activities. We'll increase the crew and ground mission autonomy. We'll include communications delays more typical of Mars missions. We'll incorporate exploration-related system experiments, and then potentially add exploration tasks to post-landing activities when the crew comes back from space station. In the 14-15 time frame, again, more rigorous, longer periods of autonomy, incorporate more exploration-related system experiments. The MCC oversight will get modified to allow for more autonomy while still, of course, protecting the space station operations. And then the hope is to incorporate some post-landing, maybe multi-day exploration using the analogs. So when the crew comes back down from space station, have them execute some landing activities they might do similar to a Mars landing. And even potentially in the future, launch them again to simulate a return to Earth. As you can see, around the post-2015, we'll actually look to do an actual transit to Mars as rigorously as feasible on the space station, progressively increasing comm delays to mimic the Mars approach, look at onboard science to be compatible with Mars-like mission parameters, and then again expand that post-landing capability. So some notional possible objectives. Again, this is notional. The planning phase for this is still in its infancy, but we want to conduct Mars missions in taking a look at the launch, transit, and landing phases. We want to work to develop an integrated strategy for conducting joint exploration missions with roles and responsibilities, using it as for a model for the actual mission. Work with the study teams to ensure that the priorities are correct and they're being addressed. Look at pre-flight preparation that would go into a real-time mission, and that would include a mission management team function, flight design, crew training before they would actually launch, flight procedure development, flight software development, and then, of course, certification of readiness. Kind of simulating these steps to help us think about how we might be actually doing this for the actual mission. And then the real-time mission would use the ISS confinement in zero-G to simulate the crew activities during long-duration flights and crew arrival at Mars. And the idea would be to better understand the effects of isolation and confinement in zero-G. So we would talk about closing the windows to have that loss of Earth visualization reference. The effects of zero-G with physical deconditioning on the Mars landing transition. The impact of comm delays, workload planning, scheduling and training, medical, behavioral, and psychological support requirements, and then flight control team requirements, analysis, and science team support. This is very notional, very notional. I want to emphasize that. There's still lots of questions that need to be addressed here. So these are just the beginnings of what we're thinking about. Some of the key questions, obviously, that need to be addressed is the number and schedule of the preparatory simulations that we're going to conduct on space station. Then the simulation duration, how long is it going to be? Is it going to be a standard expedition increment, or are we going to look to do something for longer than that, closer to model what a Mars mission might be? The crew size, who's going to participate? How will that be done? How will the crew be isolated? You know, obviously we're not going to be able to fly a module as large as the overall space station to Mars, so we're taking a look at how that can be implemented. There's another analog program within NASA, the Deep Space Hab module, that's looking at something like this too, potentially maybe flying a module to space station, or maybe utilizing one of the existing modules like Columbus, for example, and try to isolate the crew that way. We'll take a look at the scope and implementation of that comm delay. Clearly you want to simulate comm delays as realistically as possible, but you have to acknowledge the space station is designed to be a real-time access, so clearly you're not going to turn the space station into a delayed communication facility, but there are ways to simulate that. What sort of international partner will be participating? We want to take a look at how you would simulate and have real flight control teams to make sure the space station is operating, and yet we're simulating a Mars mission using the mission control team. What the Mars mission timeline might be, and then post-landing objectives and implementation. So these are the big key items that we're looking at to conduct this simulation. We're hoping to get a lot of insight from the work that the Russians have done, in particular with the Mars 500 program. We'll be supporting that symposium next week to help get information from that to incorporate into what we're trying to do. So this is kind of a layout of what's happening over the next couple of years for the overall analog program. You can see RATS and NEMO and the in situ resource utilization activities. ISS is down, or sorry, the iStar piece is down below, and some of the key objectives we're trying to accomplish in the next year in 2012. And then on to 2013 and 2014. This continues on with some activities that we have. iStar also is following this with more complex, operational scenarios using the space station to try to help reduce those risks on exploration. As far as the strategic plan goes, the idea is to use a phased approach to reduce the exploration risks and to address those architectural questions. We're going to start with short duration iStar analogs, and then establish a baseline for crew performance, behavior, medical procedures, develop and test the countermeasures needed for that. And then we'll gradually increase periods of crew and vehicle autonomy simulations. We'll help with the crew procedure mission control operations to modify them to be a more realistic experience to what will be done for a deep space mission. We'll use the exploration technology and incorporate more realistic communication delays to simulate that Mars transits to, we'll try to do that before 2016. And then again, as I'd mentioned before, look at the possibility of post-landing exploration mission analogs to be added. That's obviously not trivial. How we would implement that, and the keeping the crew safe, keeping the crew healthy, and still yet trying to meet all our objectives with the international partners as well. So that's what iStar is in a nutshell. We're looking to help mitigate the risks and challenges facing astronauts on the long distances to the asteroids, the planet Mars, or perhaps destinations even further from Earth. That's all I had.
Scott?
Thank you, Sam. I appreciate the opportunity to be here today. My name's Scott Copeland. I'm with Boeing. So I'm responsible for integrating all the payloads that NASA is sponsoring, as well as the ones from George's office and for the DoD onto station. As George stated, station gives us a great platform to do some research. We've got components that are pressurized and unpressurized. I'm not going to talk a whole lot about some of the experiments that are currently going on internally, but we do have 3 racks that are dedicated to human research. So I don't have any charts on those, but there is an entire program that's dedicated to that would be applicable for exploration as well. I do have several items I want to touch on. that we're currently working that are associated with the external platforms, and as well as some future applications for consideration that Boeing's working on. So the first payload, it's been a very successful payload. It's called the Materials International Space Station Experiment, MISSE. So far there's been 8 MISSES flown over an 11-year period. MISSE 8 is currently on orbit now. These have been located throughout different areas on the external of the space station. But it's looking at the combined effects of atomic oxygen, ultraviolet, direct sunlight, radiation, and then the extreme heat and cold to enhance material development. We've seen a lot of changes through the years with this over the 11 years. The first samples that were returned, we saw significant degradation. Samples were then changed out. We made process changes and such. And now the samples are coming back with very little damage. So a lot has been learned through the years by using MISSE. It's fairly inexpensive as far as what it's cost to put together. I think the total investment's been under $100 million over the 11-year period to date. The estimated return on the investment has already been $2 billion in research and the savings that it's brought in bringing new materials to market. It's envisioned over the next 10 years that will grow by another $2 billion, resulting in about 40-to-1 return on investment. So kind of the con-ops for MISSE. These are small sample trays. You have numerous samples. Over 1,500 have been flown to date. So it's basically a suitcase. These are been carried outside by EVA, and then they're opened up and exposed. And after a certain planned period, then the crew member will go back out, close them, and bring them back in for return. Now the future MISSE is going to be all robotic. There's several concepts in development now that MISSE X will be able to change samples robotically without requiring EVA. So I know that team is looking for people to participate. So if there is some interest, I'm sure George or myself can get you connected with the proper folks there. Got a short video I want to show from I think it was MISSE 6 when they brought the samples back and when they first opened it in the clean room. Well, unfortunately, that's not working here. But anyway, they've in the video you can see the samples were very well maintained after several flights. They are able to make adjustments, repeat their experiments, and get better materials. Another payload on the external is the remote robotic refueling mission. I think George mentioned this earlier, but this is it's got significant impacts for exploration. It's able to use the robotic arm and a set of tools to show how you could refuel satellites or spacecraft in orbit. This is being done by Goddard with work with McDonald Detweiler, who's here today as well. But already seeing good results for that. It's on orbit as we speak. The demonstration task really has 6 things. They're looking at being able to remove the launch lock, gas fitting removals, being able to actually demonstrate refueling, be able to grab the thermal blankets and lift them, removal of screws, and electrical cap removals. So to do that, there's, I believe, 4 separate tools, so they're multi-purpose tools that are used. You can see the tools here installed in the interior of it. On the external surfaces, they have the different connectors and different scenarios that they will interface to do the demonstrations. Okay, another one that we're currently in the early stages of integrating on the station is the Bigelow Expandable Activity Module. This is an inflatable, but it certainly has direct application for exploration. The term for this is called beam, but they're looking to demonstrate that technology on the station. There's currently, I believe, two free-flying inflatables that Bigelow has already flown to date, so those are in orbit now. This one will be attached to the pressurized volume. It's going to be a closed-hatch operation. The current scenario is we would open the hatch 3 to 4 times a year just to do some inspections on the interior. He does have a few devices, technology devices mounted on the interior, but no major payload operations or activities going to be going on. Okay, some other potential uses for station that could be used for exploration. One is for the solar electric propulsion that Dr. Gardini mentioned earlier today. This particular one, Boeing has been using the Hall thrusters on their satellites for many, many years. These were first invented, and they're up to TRL-9 since 1971. The Russians were in first use. There's been no failures of these to date. We currently have over 124,000 cumulative hours of use using these Hall thrusters. There's over 34 satellites that are in use right now with the Boeing products. So advantages for ISS, the low wear and tear, they're very high reliability. It'll reduce the logistics for refueling for the propulsion, and it's got a direct application. And what we want to demonstrate on station is use of a cluster. So far, these have only been single engines, not used in like a 4 to 6 cluster configuration. So that's what we hope to convince NASA to let us demonstrate this using station. So those discussions are in work. It's just a concept at this point. So what we would do, we use the robotic arm. We would place these out on P5 and S5 and use that, as you can see here, to do on-orbit boost maintenance. Another component to make solar electric propulsion a viable option is we have to show improvements with our solar cell technology and solar panels. Boeing has successfully ground demonstrated solar concentrator technologies, and we're using thin blankets. You can see here, here's a deployment demo that's already been done. We've done testing in the sun simulators, and we're currently looking for a flight demonstration of that. But high efficiency solar panels are certainly going to be required for deep space exploration and in order to get higher power with your solar electric propulsion. So kind of historically where we are here, we started with the Boeing 376 solar electric power. It was only in the 1 to 4 kilowatt range. We're up to the 25 kilowatt range now through 2020. And we envisioned over the next few years getting up to 1 megawatt. Okay, so the two main components to make solar electric propulsion a viable option for deep space probes or for crewed vehicles, you have to have, we think, clustered use of the engines as well as the high efficiency panels. We integrate those together. We want to have a 30 kilowatt flight demonstrator product here in the 2014-2015 that we're currently working on, and then a 300 kilowatt operational system by 2020s. I think everyone has touched on this. This is one of our most challenging areas right now on the space station, the ECLSS systems. We've learned a lot. There's technology demonstrations that George Nelson's office has been involved with for the next generation for the CO2 removal. But we've certainly had challenges in this area. And right now, we certainly have to fly back and forth spares. But we can see that this is a great opportunity to use ISS for advanced ECLSS, and certainly going to be required when you don't have the capability to come back to Earth easily. The key areas for development would be CO2 removal, oxygen generation, the urine water processing, CO2 reduction, trash volume, I think trash was mentioned earlier, particulate and microbial fungal control. So some of the lessons learned on station already in the early days is the hardware does not work the same on orbit as it did here on the ground. We didn't generally have a lot of hours to do ground testing on this hardware, so we've had some surprises that we've had to be able to react to. The system performance trending effort, we get lots of data, but it's a lot of data to go through and try to figure out what's going on. So kind of in summary, one of the items I didn't mention, but I think it was talked earlier about the signal latency. So there's some ongoing effort now at Johnson, some technology demonstrations here to simulate the delayed signal, which will be important for deep space exploration. But the single Hall thrusters, we need to get a demonstration of those using multiple clusters. We plan to do that through the concept of the warp that we talked about. We have advanced ECLS. We can integrate that with advanced solar panels, and then we develop a space tug and on for manned cargo. So thank you very much.
Thank you, Scott. Ito-san.
Okay. Thank you, Sam. Hello, everybody. My name is Ito. I'm very glad to join this conference from JAXA. My job title is too long to say by myself, but I just work at the JAXA ISS program office and work for maintaining the JAXA's technology roadmap for future human space mission. Today, I would like to explain the JAXA's utilization of ISS Kibo. Kibo is a nickname of a Japanese module as a testbed for future mission. JAXA has successfully developed the first Japanese manned space facility Kibo and the first cargo transportation system Konotori. Konotori is equal to HTB. And its operation has started in 2009, about 3 years ago. We have acquired core human space technologies through the development and operations, but some essential system, for example, air revitalization, still rely on the US segment. So as a next step, JAXA's human space program is further proceeding technology development to enhance its capability for human space activities. We highly prioritize human health, life support, and habitation as the key technology for the next step. JAXA would like to make use of the Japanese asset Kibo and Konotori and the characteristic of ISS, for example, continuous long-duration operation orbit, stable operational resources, potential collaboration with international partners. And we would like to carry out a technology demonstration of this focused area to enhance Japanese space technology. As JAXA's high priority candidate of technology demonstration, we have especially trying a development which could exceed the current performance level of the existing device on the ISS in preparation for the future missions. Air cycle and water cycle and radiation measurement and suit assembly, they are the example. And we try to apply cutting-edge technology in Japanese industry to those technology development. We have already started ground research and targeting element level demonstration on board by 2015. I'm going to explain the technical features of those technologies. The first item is the air and water recycle technology. I think every agency is challenging, but JAXA also would like to try it. That is a core technology of life support, and in Japan, the water and air cleaning system is very popular and widely spread. More than 90% of personal residences in Tokyo has own water purifying device, and I think it is well known that the Japanese manufacturer is good at making compact and light and low power consumption products. So we'd like to make use of the excellent technology in commercial field and develop an upgraded product that could be used in severe space environment. Now we are on the ground research phase, and regarding the air cycle, we're targeting recycle 80% of O2 of carbon dioxide, and it's about I think it's about 10% higher efficiency than the existing system. And as for water recycle, we are targeting more than 90% recovery rate with NASA potable water and standard tap water quality. Furthermore, power consumption is 1/3 and weight is 1/4 of the existing ISS system. That is our target. The next one is radiation measurement. We think the radiation measurement and protection is one of the important and difficult technology for human space exploration beyond low Earth orbit. Up to date, space agencies have located dosimeters on ISS and space shuttles, but the performance is the conventional dosimeters are limited. It could monitor only charged particle, and its measurement accuracy is not enough. Real-time dose measurement technology is must for long-duration human stay in space. However, it has not been established. To realize such function, real-time and simultaneous measurement of absorbed dose and linear energy transfer distribution are necessary. Evaluation of exposed dose for human being requires those data. So the name is JTAPEC we are now developing, is the first active dosimeter to realize such function. Also, the measurement accuracy is less than 30%. We are going to launch 2 detectors in 2014 and start measurement. The next one is EVA suits assembly. We are trying to use Japanese unique sewing technology to significantly reduce EVA prep time. We pick up the four-way weaving technology and the seam-free knitting technology. Normal clothing we wearing is often the 2-axis weaving, but 4-axis. A good example of 4-axis weaving is carbon fiber reinforced plastic. It is used in the latest airplane and something like that. It is very light and strong material. And the seam-free knitting is if we want to make the whole garment, we first produce the parts, each part, and connect by sewing. But this technology can make a whole garment seamless whole garment. This technology could provide good characteristics to garment, high flexibility as well as high strength for twist, and even if crack happened, it will not extend. Generally, if the internal suit's pressure is high, its flexibility is lost. But owing to the new material, the suits can keep good mobility even in high pressure. The high pressure suit can eliminate EVA pre-breathe and significantly reduce the EVA prep time. We plan to expose the new material of EVA suit to make sure its tolerance in space environment. And we have ground test of EVA suit assembly in 2015. The next topic I would like to explain is technology demonstration capability on Kibo exterior. Kibo has a airlock and a robot arm and exposed facility, and they located very closely, and cooperative operation can provide a good opportunity of technology demonstration in exposed environment. Let me introduce an example of the demonstration capability. The first one is JAMRMS utilization. JAXA prepared the experiment adapter, which will be grabbed by JAMRMS and provide an interface to experimental device. An experimental device is launched as a pressurized cargo and transferred to the exposed area through JAM airlock, and experiment while retained JAMRMS. The example of demonstration are material exposure and the device sensor test with changing direction by robot arm manipulation. And in addition, JAXA developed a small satellite deployment mechanism. It will be used for pico nanosatellite deployment, and also it might be utilized for small free flyer and re-entry test. And the second one is JAM airlock utilization. On the airlock table configuration, we plan to use this capability to expose material device sensor test which does not require any direction or location setting with JAMRMS. And into an airlock configuration, we use the airlock as a vacuum chamber in space. We have demonstration which require only microgravity and a high vacuum environment. The third one is extravehicular temporary exposure. Now we are developing a sample exposed equipment. The size is 10 centimeter square. It is very small, but this equipment can load 20 small samples. It will be installed in handrail by JAMRMS small fine arm. The location is highlighted here. The equipment with samples transferred through airlock and located temporarily in exposed area and recovered to pressure module after the experiment. I forgot to say one thing. The most unique point of the demonstration capability on Kibo exterior is that we can various type of demonstration without EVA. The experiment device can be launched as a pressurized cargo and transferred to the exposed facility through airlock and recovered to the ground. We believe this capability on Kibo exterior is very useful for demonstration for future space exploration. This is the final chart. Finally, I would like to show a brief proposal to fully utilize ISS as a testbed. Firstly, we should promote international cooperation. We need to share and exchange information about technology demonstration capability on each agencies and technology development plan among ISS partners. The advantage of the unprecedented ISS partnership should be utilized more, so that the limited funding could be concentrated on development of leading edge technologies. JAXA hopes the capabilities on Kibo exterior will be used by other partners to fulfill various and efficient demonstration. Secondly, we should have a framework to gain crew time for technology demonstration. At this moment, one of the severe constraints of ISS utilization is crew time. Crew time allocation for system operation and utilization is re-evaluated to generate crew time to accelerate technology demonstration for space exploration. Thank you for your attention.
Diego. Need some tech help to get it connected.
Or back here.
It's going to be connected to a Mac.
That's to a Mac.
Yeah, I have the. You have the adapter. Okay, great.
We can probably have we can replace one.
Perhaps it can make it here.
No, not this one. You could also use this one here. This is mine. Just make sure I'm not plugging the whole auditorium.
Should do. Thank you. Maybe you need to switch to the screen. Alright, detect. Oops. I guess I could get a USB stick. Oh, maybe did it? No, it didn't. Unplug. That's the source? That's a... Yeah, that's the correct one. We used it to... What do you think we should do? Always with the videos. Alright. There you go. It's huge. Yes.
We got the technology.
All right. Okay, sorry about that. Perhaps the frame doesn't get everything, but I guess I only have mainly pictures, so it should be okay. Well, my name is Diego Urbina, and I'm a consultant at the European Space Agency. I was a crew member in the Mars 500 simulation mission that took place in Moscow from mid-2010 to November 2011. We were enclosed in 6 people in a series of pressurized models at the Institute of Biomedical Problems, simulating a round trip to Mars and see how what psychological findings we could have, and what physiological findings, with the exception of microgravity and radiation, we can find about it. Also, some operational issues. There has been recently some buzz on the news about the Americans wanting to do something similar to Mars 500 on the ISS with the ISTAR office, and also the Russians would like to implement what we learned from Mars 500 on the ISS. The advantages of doing it on the ISS, of course, there's microgravity. There is some radiation, not exactly the radiation we have on a trip to Mars, but similar. And well, also learning to operate a multi-billion dollar or euro complex with the constraints of the delay of communications, for example. This is our crew. There you have Van Yue. He's a physiologist from the Chinese Space Agency. Alexander Malievsky, a doctor from Russia. Roman Charles, mechanical engineer, is a crew member from France. Sukhrov Kamolov, he's a Russian doctor. Alexei Sityov, our commander, he's a Navy diver from Russia. And yours truly, I'm an electronics engineer from Italy. These were the models in which we were confined. You have we had a 150 cubic meter module, which was the one in the middle, which is the one where we lived, and we well, had the galley and the place where we entertained. We had a medical module, which is on top. It's 100 cubic meters, and that's a place where we mostly conducted experiments. And we had a storage/gym module where we stored all the payloads and stored all the equipment that we had to use. Later on, we would when we would reach Mars, we would be able to open a model that you can see there. It's a landing model. And it was full of items that we would need for the second half of the mission. We couldn't open it during the first half of the mission. When we reached Mars, we could open it. So some of the questions that have arisen is, do we conduct a Mars 500-like simulation on the whole ISS, or do we isolate one model? This is a big logistical question. The Russians have proposed in an early brainstorming phase to do it in the FGB-2 model, which is the Nauka model, which is fairly autonomous, and you could hold a crew there. Personally, I think it would be pretty tough for a crew to be in there, but it would mimic the psychology the best than running it on the whole ISS. That, as you know, is not necessarily. Sorry about that. Is not necessarily, as has been said before, it's not. It's a facility designed to be operated in real time. One of the things that the psychologists have thought about is that, well, for Mars 500, it worked pretty well. The crew got along very well, And most of the success of this was the fact that we were selected first on an individual basis, but later on at the end we would be 10 people, and we would train all together, and the psychologists would analyze which group got along better, and then they would pick the final crew. So this is something that you currently cannot really do on the ISS because the agencies propose the crew members and just pick the single individual. So the psychologists think it would be helpful to choose a group. Food in the Mars 500 mission. During the first half, we had a German experiment which aimed at controlling, checking our sodium intakes and the sodium that got out of our body. And it was pretty tough to run it because we had to eat everything on the menu, completely everything. And we couldn't leave anything out, or we couldn't add anything, so it was really rough. So during that half of the mission, like, our main topic of conversation was the food. Then we went to Mars. We got access to some Russian space food, the same that flies on the ISS, and it was nice to have this change. And during the second half, we had a little bit more freedom. Of course, we tended to a little bit consume a little bit more the things that we liked. So at the end, for example, if everybody liked Snickers, at the end there will be no Snickers in the spaceship. So there are many little things to consider with the food. For example, also with foreign crew members, for example, the Chinese, which is a completely different culture from ours. Perhaps we have more in common with the Russian than with the Chinese. So for those very different cultures, I think that it would be a very good idea to have personalized menus and things of the sort to endure the isolation of a trip like that. Exercise is also a big deal. In there you can see some experiments that we run before exercise and after exercise. We had EEGs and filled some questionnaires to see if it could be used also as a psychological countermeasure, and indeed it worked a lot like that. We were relying a lot on exercise to feel better during the day, so it was very important. When, for example, considering if you want to isolate a group of people in one single module, it's important to know that perhaps they won't have the same countermeasures as the people that would be in the rest of the ISS, so it will be a little bit harder for them. There are several experiments that were run on Mars 500, but they have also their counterparts on the ISS. So I think that we give a lot of valuable input because we have the data from Mars 500, we have the data from the ISS. For example, these are some panels with antibacterial coating given by Thales Alenia Space in Italy that aim to see on which panels, which antibacterials work better. Bacteria are known from the mirror years to be sometimes hard on some structures, like for example the cables. They tend to eat cables, so it's important to analyze this in a confined environment. So this is the one that they run on the ISS. It's called Viable. We had as well greenhouse experiments. These are some educational greenhouses. We didn't grow anything to eat there. They were used for the greenhouse in space ESA outreach experiment, in which they were raising plants in the ISS and also in Mars 500. But we also had some real greenhouses where we got a little bit of sometimes tomatoes and these types of things. We didn't get a lot of throughput in these greenhouses, but they were definitely very good for the crew and very convenient to have every once in a while a little bit of fresh tomatoes. We would eat them like in a nanosecond, but they were very good. So there you see the Lada greenhouse that perhaps on the ISS, I don't know if the astronauts are allowed right now to eat the food that they can grow there, but it would be useful if you did a simulation of a trip to Mars to have that. We had some simulations of very important ones that, for example, they removed the electrical power. We didn't know it was a simulation. We thought it was real. And that is something that you almost certainly you cannot do on the ISS, not telling the astronauts that they are out of power. So that is perhaps some difference, that you cannot run this type of simulation on the ISS. Of course, in there you have the real situation. You encounter real problems, but perhaps you will not be able to test how the astronauts react to the very big problems where they are isolated from Earth because of safety reasons. You cannot do this on the ISS. Recently, the ATV docked to the International Space Station. It was nice because a part of the crew was in the ATV control center, and it was really cool. It a little bit reminded us of when we got to Mars. The mission profile foresaw that there was that model, the landing model, had been sent before to Mars, and it was full of this things for the second half of the mission, and we just dock to it and get the stuff. So it reminded us a lot of that, of those moments. It was the most important moment, like the best moment that we had in the whole simulation, because that model had stuff that had been left by our family and had new food and had new things. So in some sort we had a resupply that, well, when you run a simulation on the ISS, you are most likely not able to just cut the supplies, cut the progress, cut the ATVs. So it can be used as a part of the mission profile that you have this model where you had hidden stuff that couldn't be opened until some date. We did a series of rover drives on the Martian surface when we got to simulated Mars. And to test, well, the robotic operations by the crew, mostly cognitive and performance, as a cognitive and performance test. That's how we run this robot after 8 months of isolation. The European Space Agency has a project that is called Meteoron, that is it aims at controlling a robot from the International Space Station, very similar probably to what they're doing at NASA, of controlling a robot from the station. And this could be incorporated also in the mission profile, as when the crew gets to Mars, they start operating this robot, and they can also be used as cognitive tests, but with a real robot, as well as to test the technology. We did a series of simulated extravehicular activities on the Martian surface. Fortunately, I think the video doesn't work. Murphy's Law. And it was very, very interesting moment. It provided a lot of new activities, new things to do. So it's a very exciting thing that the crew can look forward to in a Mars mission. Perhaps we will need to study a lot how to deal with this type of extravehicular activities, be it planetary or also microgravity EVAs on the ISS, perhaps running simulations at the NBL or at the MBF of Europe with a very limited support from the ground, and then extend these, if they work, extend them to the ISS to have some EVAs with not a lot of support, only from the intravehicular crew possibly. The second half of the mission, after we did Mars, was very, reportedly by some of the crew, was the most monotonous part of the mission, the hardest, because we had already reached Mars, and then we had to come back to Earth, and there was like a year had passed since we saw our families, and then there were 7 months or so left, so it was really tough. So this brings us to the importance of psychological support. It's very important you have a very reliable person on Earth taking care of all the problems that you may encounter with your family or work-related problems, and you don't have to have this in your mind too much. And so in Mars Behind we had some really good psychological support, at least on the ESA part. So that's something we can learn from. Well, of course, we had our techniques to deal with monotony. I don't know if you can see, this is our Halloween party. And, well, we just used any chance to celebrate whatever there was, like birthdays or Halloweens or Christmas. So we had even different New Years, because in China they have different New Years. We had different Christmases because in Russia they have different Christmas. So we celebrate absolutely everything. And it's nice to know that also on the ISS they are adopting these countermeasures. Like this is the Halloween at the ISS, I think. This is one of our birthday celebrations, and there you can see that there's some gifts. The psychological support had hidden some gifts on the model, because not being there any resupplies, it was hard. I mean, we couldn't not just go buy a gift for our crew member. So we did that. We just picked the hidden gifts, or we simply got the food from the storage module, and like the favorite food from this crew member, and you put it on the table and at breakfast, and that is something for them nice to find. So you have to come up with these little tricks to avoid monotony. This was Valery Polyakov. This is the person who has spent the most time in space in one single run. And this is a video message that he sent to the crew when we reached 437 days. And it was very nice. The Russians had got a lot of experience in long-duration space flights, and they affirmed that based on Mr. Polyakov's flights and other astronauts' flights, that they could assure functionality of a crew member even up to 1 year and even more. So with the countermeasures that are in place, so that's really good. It is a known fact that Valery Polyakov wanted to, when he reached Earth, like he did a lot of exercise in orbit, and when he reached Earth, he just wanted to walk. He told all the people that were picking him up that he wanted to walk, and he walked, and he demonstrated a little bit that humans could walk on Mars. Of course, if we send some people to the ISS for a long, extreme long duration mission, we're going to be able to have more data points and to see how this is true on more than one person. The delay in communications was both operational and personal. So perhaps we should look into how the crews will receive that. Like, are they willing to give up the satellite phones that they have right now and the internet that they have right now? They just got it like 2008, and they're just going to cut it again. So so if we want some psychological data, I guess this would be a nice thing to have. But it's extremely tough because we're so used to it. We're so used to having cell phones, to have iPhones on Earth. When we go out there, we want to have like the most that we can, and we can't. So we had in Mars 500 we have this series of data packages, and I was in my free time I was basically programming software to make the most of the use of these data packages, like packing my emails real quick, or for example, I wrote a software that that they installed on a computer on Earth, and this software ran on this computer that had access to the internet, and I sent this software a package of the websites that I wanted, and they give them to the software that is on Earth, and it downloaded everything. And so that was a really nice thing to have, also a thing to spend my free time on. Some more considerations you want to have. There's good clarity and transparency, because people in isolation are really, they really crave on that. It's a big interest in the crew. Also, a big balance between a situational aware crew and an irritated crew. They didn't want to irritate us too much with some things, but we wanted to have as much information about what was going on Earth as possible. So there has to be a lot of work on that balance. The responsiveness of the ground to the crew. Sometimes there was the delay, yes, but also sometimes our requests were sitting on a desk just gathering dust until somebody decided to answer. So it's very important to have good responsiveness, so the delay is not felt so much. Availability of onboard resources that facilitate the crew autonomy, like a lot of information on the spacecraft systems, on everything. It has to be uploaded to the ISS. And as well as for personal purposes. I before going into Mars 500, I downloaded the whole Wikipedia, and that was the most useful thing, at least to solve some arguments about some discussions. and very good balance, and full the crew time as much as you can, and have very meaningful tasks that the crew can feel like they're important. It will be a logistically complex endeavor, simulating the interplanetary mission. Of course, with the limitations of the ISS, of the real-time versus the delay, there has to be some things that we have to give up scientifically that we cannot really achieve, but there are some other big advantages. Also, the delay in the communications equals time, equals money. Some payloads are there, and if we have the operational delay with the payloads, it's going to be a problem and a loss of money for some people. The operability of current payloads, we are going to have to think of new ways of designing new payloads that can be installed autonomously by the crew and maintained autonomously by the crew, which is not necessarily the case right now. And possibly the best psychological simulation would be locking the people in the models. Also, it would have a lot of logistical complications, but it's the best way. If you want to simulate, well, the physiological effects, it might just require to send some people up and working business as usual on the ISS during an extended amount of time. And well, the operational simulation would just require the insertion of the progressive delay, as for example, what ISTAR wants to do. But in any case, it's a good idea to make this change progressive and not just in one step. And well, this is a picture from the day that we landed, also known as the best day of my life. So I thank you very much for your attention.
Thank you, Diego. Okay. Okay, we got lunch waiting, so we have a few questions.
Just curious, which language did you use?
The two official languages of the mission were Russian and English, but at the end, between the crew, we ended up talking Rozgish.
Thank you.
Anyone else?
Sam, we got one for the panel from our Twitter feed. It was, to what extent are 0.38 to 1G tethers or other artificial gravity solutions being considered as viable to mitigate zero-G effects or risks?
Now, well, within the ISS program, I don't believe we're going there as far as artificial gravity, and I personally do not know where the exploration architectures or DRMs are related to that. We have done experiments on space station and shuttle related to the microgravity effects on plants and to some extent on animals as well, but nothing related to variable. We do have centrifuges on board, but they're very limited in that capability. One more. Lunch, anybody? Thank you.
Thank you very much. As Sam said, lunch is right now outside in the Explorers Hall with Pete Warden speaking, and after we eat.